So, good morning, everyone. So, as I was presented, my name is Mikael Holmberg, and this session is about ExtremeFabric. So, this is kind of a general session around Ethernet fabrics. My intent is to walk you through what the extreme picture of the fabrics are. Now, to kind of put you on the map, this is going to be a pretty technical session, so I'm actually going to walk you through the fabric architecture, how the fabric is formed. I'm kind of going to compare it to some other fabric architectures. Truth being is that the fabric is, Ethernet fabric is not a new thing, right? It's, it's been around for a while. You have, numerous vendors out there with a variety of different fabric solutions. So obviously, Extreme do have a solution for that one as well. So basically, what you see is on this slide a definition of the fabric. So I think, from kind of on a high level, understanding what the ExtremeFabric is all about, it's a fully measured automated fabric based on layer 3 that provides you with host routes for IP mobility for end-to-end connectivity. And this is done based on layer 2 with the VXLAN overlay, based on layer 3 with the VRFs. So this is kind of creating the picture for you. Obviously, this is a high level. So what I'm going to do is walk you through kind of the fabric architecture as such. Before we actually get that far, I need to kind of show you a disclaimer. So I'm actually going to talk about some stuff that's roadmap items, some stuff that's in the pipeline, which means basically that the fabric story is going to be delivered in multiple phases. Okay, so this is kind of the agenda on a high level. So I'm going to talk shortly about why the Ethernet fabrics. We are going to look at architectures designs today, which kind of builds the story around why you actually want to have a fabric architecture. Obviously, that correlates to the ExtremeFabric. So basically looking at that then from Extreme's point of view. And then I'm going to walk you through a couple of architectures based on spine leaf. And then obviously, you kind of saw in the previous presentation already the 870 Summit. So that's part of the design as such. So obviously the 870 being one of the switches, the 690 being another one. So with that said, let's start to dig into the stuff. So I think there's really nothing new on this slide for you guys. This is kind of the old way of building networks based on a three-tiered architecture, based on basically something called a fat pipe, which basically means that you have your edge layer, aggregation layer, and your core layer. Now, this is ideal for north-south traffic, but it's not ideal for east-west traffic, which obviously means that you need to have traffic traversing from south to north to basically do a U-turn right. So assume that you want to have east-west traffic. You always need to go, starting from the axis, going up to the core layer to basically do a turnaround again. You need to introduce something like spanning tree. I mean, spanning tree has been out there for ages, right? Which basically means that you are going to block some links, which is not ideal. So as said, this is like the way how you built networks in the past. Now, kind of correlating with this. So as my topic is really about fabrics, and obviously, one thing being the spine and leaf architecture is that, if you look at the switch hardware today, what you can see on this slide is, the BDX, which is the flagship from Extreme, is the big fancy chassis-based box, which obviously, gives you like 2.56 terabit switching capacity per slot. Now, if you start to look at new hardware, like the 870, which you can see is actually 3.2 terabit in a 1RU form factor, which basically raises the question that do I still want to have those big fancy boxes? Because of the fact that, fixed form factor switches actually do give you even more performance today, which basically leads to the question of what if I start to look at an architecture actually instead of having a big box where I basically have my I/O blades and I do have my switch matrices. I have some kind of connection in between, a backplane. Now what if I actually virtualize that one? I go into a spine leaf architecture, saying that my leaf is the I/O blades, my spine is the switching matrix. This would allow you to actually, do a lot of things, like ISSU. This would obviously be also associated with the cost because of the fact that, a small fixed form factor switch is, or the price for that one compared to a big fancy chassis is completely different. So there are some, good pinpoints hardware-wise why you actually want to start to look at the spine leaf architecture. Now, to back up this, here's a couple of interesting things. If you look at this slide, you can see that, Deloro, the prediction is actually that, as you can see on the right-hand side, the modular switches sales is declining. So 0.8%, saying that year after year actually is declining, while the fixed form factor is actually increasing. So once again, you basically have the analysts saying the same thing, that this is from an industry point of view. This is not extreme specific. This is from an industry point of view, really the fact of, how they see the hardware. So once again, the chassis based compared to the fixed form factor. So this kind of makes sense, to start to look into a spine leaf design and obviously a fabric design. So, kind of looking into spine leaf. So obviously, what this gives you is obviously far more scale. You only have 2 layers to traverse. And you have actually multiple active links, as you can see. Now, there's a need for actually some kind of a protocol here to actually allow you to have active, active, active. So as you can see in this picture, you have 4 spine switches and n amount of leaf switches, which means that eventually you want to have all your leaf connections into the spine being active. Now, if you start to look at this from a protocol point of view, you guys probably are familiar with things like Trill, things like SPB. There's a variety of different other vendors, QFabric, FabricPath. There's a lot of different fabric technologies out there that would actually utilize all the links or would actually allow you to have all the links active. So there are technologies out there to do this. Now, obviously, many of these technologies are kind of proprietary. So if we pick, for instance, Trill, how many of you know of Trill? So Trill uses ISIS underneath, right? Which means that you can do equal cost multipath for that. SPB uses ISIS underneath, right? You could use equal cost multipath for that. Now, here's the thing. Both Trill and SPB actually, from a standards point of view, allow you to have 16 ECMPs. 16 ECMPs. That's max. So you actually start to look at vendor-specific things for scaling up to more than 16 ECMPs. As mentioned, a couple of vendors, previously, those might be, capable of that one. So, starting to actually look at what once again, the analysts are defining or the standards are defining as a fabric. So if you read through this slide, it basically says it's an interconnect switches over a single logical layer 2 or layer 3 domain. Okay? I kind of walked you through that layer 2 being kind of the Trill path. You have a data plane being layer 2, and then you have like your ISIS underneath that. SPB, the same thing, which kind of raises the question about scalability from a layer 2 point of view. Suppose multiple active paths and fast failover. As I mentioned, equal cost multipath, multiple active paths. use zero low-touch provisioning. So here's a key. Now, assume that you actually have a fabric that you just start to connect elements into the fabric, and the fabric forms itself. This would be ideal due to the fact that it's zero touch. You don't really need to touch the fabric. It just starts to do some kind of a signaling to form itself. And then you basically look at, a variety of topologies, leaf spine, mesh, so on and so forth. So once again, this is, from an industry point of view, how a fabric is defined. So that aside, let's now actually start to look into ExtremeFabric. So my intent is to actually kind of, reflecting on what I covered so far from a high-level standards point of view or, analyst point of view, look how our fabric story actually are looking into these different aspects and what it would actually deliver for you. So on a high-level definition, it's, ExtremeFabric is a network of cooperative interconnected devices that create a fabric of any scale for any topology. Now, it provides, fully redundant multipath routing, and the fabric itself is based on host routing. So this is a key. It's a layer 3 fabric based on host routing, which means that, it's /32 or /128, depending on IPv4, IPv6. So this is the high-level kind of definition of fabric. This is pretty abstract so far, but looking at the summary for this one. So once again, keep in mind what I was kind of talking in the previous slides in regards to what the industry as such is seeing a fabric being. So zero touch, zero local configuration, which means that I have a mechanism in place that once I start to add elements into my fabric, these elements would start to form the fabric. Okay, sounds pretty cool, right? So how is this done? So we are actually using, well-defined protocols that has been out there for a while. We use LLDP, we use IPv6, and BGP. These three things are actually more or less the foundation for the fabric. It's based on a RESTful API. So you guys probably know that CLI is kind of gone. That's back in the 70s. So it's really based on a way of having a RESTful API that would, manage and configure the switch. The same basically applies to policies. So any policy you want to actually map to the fabric or map on the access side, that's done with RESTful API. Now there's something called the one config, which means that you have basically the same metadata on each and every element within the fabric, which basically means that I have the same configuration file for each and every element within the fabric. And that's, once again, done with the RESTful API. Now, looking at the next one then, equal cost multipath. No rocket science. I mean, this is, as we have discussed already, you have it within the fabric. The fabric as such do support, 64 ECMPs by default. Now, on the attachment side, so I kind of mentioned the LLDP. Obviously, we actually use LLDP on the attachment side as well, which means that I can actually lag connections on access side into the fabric, meaning that I can connect a switch with a lag. I can connect a server with a lag. So from a construct point of view, this looks like an MLAG. So I kind of leave this for now here. I'm coming back to this later on, from a construct point of view, the MLAG, how that's seen from a fabric point of view. And then obviously you have mechanism in place where you can configure default routes, gateway, static routes, so on and so forth. Once again, this is going to be done from your management, basically, entity that's going to talk RESTful API down to the fabric. So let's start to build a picture. So we start from the access side. You can connect into the fabric directly attached hosts. You can connect routers into the fabric. You can connect switches into the fabric. And obviously, as said, the fabric is managed from some kind of a GUI based on a RESTful API. And then the servers could be connected, with a lag. So as said, this looks from a construct point of view as an MLAG. Now here's the thing. As you can see in the picture, you actually have the servers connected to two different elements within the fabric. But due to the nature of the fabric is seen as a single entity being a single MAC address, which means that even if this looks from a construct point of view as a MLAG, it's still a lag because it connects in, on a single MAC, basically, the two different entities within the fabric. And then obviously, you can have your overlay for layer 2 transport being VXLAN. So you guys follow me on this, that the ExtremeFabric is a layer 3 fabric. Everything is host route driven. If you want to pass a VLAN through, that's done with the VXLAN overlay. So having said that, within the fabric, you don't really have any VLAN concepts. You don't really have any VRF concepts. You don't really have any concepts of subnets. So to kind of build a picture, think of the fabric as pretty abstract as such. Fine. This is now the high-level view of the fabric from an access side. Now the question is, fine, how do I actually start to build a fabric? As I've been talking about zero-touch provisioning, I've been talking about, that some magic just happens because you start to connect in your elements into the fabric and some kind of a signaling is going to happen. So the first thing you actually are going to have is obviously your elements. So I'm kind of interchanging the word of elements, nodes, switches. Think of these as the same thing. So any element being a switch within the fabric. So the first thing you have is your switch elements. So what you'll have is actually LLDP. So you would use some vendor-specific attribute to start to signal LLDP. Now, once I start to signal LLDP, that's the mechanism how I start to actually discover my elements in the fabric. These elements could be, authenticated. I could use TLS. I could use, 82.1x for authenticating elements to be able to form my fabric. And obviously, you could use DHCP and kind of get node identity and IP addresses for the elements based on that one. So this is the first thing. I have my elements. I signal LLDP. Now, obviously, the fabric itself, I use LLDP with the flag set for something called EasyBGP, which means that I'm actually going to signal a BGP peer session between my elements. Okay, so I have a flag set for BGP. I'm going to basically exchange information like my router ID, my link local address, my AS number, so on and so forth, because at the end of the day, I basically want to have a BGP session between the elements. Now, for me to actually be able to get that far, I need to have some kind of an IP core. And as BGP do not do any kind of auto-discovery, I basically use IPv6 neighbor discovery to discover my neighbors and have an IPv6 link local address assigned on each and every link. You guys follow me on this? So I use IPv6 to actually form the IP connectivity. Once the IP connectivity is formed, I use the BGP. So I basically start to signal my EasyBGP and basically get a BGP session between all the elements within the fabric. So this is how I form the fabric, right? I signal EasyBGP. Now, I was kind of talking on the access side as well that LLDP is kind of a key thing. So obviously, we use LLDP on the access side for something called EasyLag as well. So EasyBGP and EasyLag, those are two kind of mechanisms we actually use LLDP for. So how is that done? What this slide basically shows you is, if you look at on the left-hand side, you see the 6th octet being the OUI subtype, which basically says one being extreme capabilities and two being ExtremeFabric. Now, if you look at the right-hand side, you can see that we use a 16-bit mask, where you can see that the first B and L bits are basically set for easy BGP and easy lag, which means that coming back to what I was saying when we formed the fabric, I have my easy BGP bit set. My neighbor have his easy BGP bit set. That would allow me to signal a BGP session between these two elements. If my neighbor don't have his easy BGP bit set, obviously I'm not going to have that element participating in the fabric itself. It might have its easy lag bit set, which means that it's actually going to signal an access connection. So for the BGP part, you basically see here that once I have my BGP session established, if any of the attributes actually change, I'm actually going to clear that session and re-signal it again. And it's just normal BGP as such. On the right-hand side, you basically see for the, your IP link addresses. You basically have IPv4, v6. As I kind of walk you through, IPv6 is the default for this one. So this is a high-level kind of view on how the fabric is formed. So key takeaway is that we use well-known standardized protocols, starting with LLDP for signaling either easy BGP or easy MLAG. We use IPv6 with IPv6 neighbor discovery to form the IP core. And that's basically the foundation for forming the fabric. We're okay with this? Follow me on this? Does it make sense? No? Yes? Okay. So, advertising host routes. So once again, as said, this is a host route-based fabric. So we actually use IPv6 neighbor and IPv4 ARP discovery to basically populate the routing tables, the fibs for IPv4 and v6 entries within the fabric itself on the access side, obviously. I kind of went through the easy lag. So obviously, requirement being is that on the access side, if you want to connect something with easy lag into the fabric, LACP is used as a signaling mechanism. Now, how many of you know BGP well? Okay, so here's kind of a couple of myths about BGP from a fabric point of view. So many people tend to think that BGP is pretty complex. Well, fact being is that if you look at it from a ExtremeFabric point of view, as I kind of walk you through, you don't really need to configure anything from BGP point of view. It's signaled based on LLDP. Now, it's difficult to configure. Well, the same thing applies. You don't need to configure anything. It's complex. Well, fact being is that many of the link state protocols like OSPF might be even more complex than BGP to configure. But this aside, from a fabric point of view, obviously you don't need to touch that in any way. It's automated. Then you have, it converts slowly. Well, we actually use BFD for that. So BFD is actually going to affect your BGP failover times. By default, BGP do not have fast failover. But by using BFD for that, you would get fast failover functionality. It doesn't support neighbor discovery. Well, I walked you through the fact that we use IPv6 neighbor discovery for forming the IP core. It's hard to troubleshoot. So here's the thing. Even if the fabric's intent is to hide all the complexity, you would have access to all your BGP commands. So you could do any trace route, you could do pings, you could do all those IP tools. In addition, obviously, all the BGP CLI commands are available for troubleshooting and debugging purpose. So, the attachment. Now, what this basically shows you is, what you can connect into the fabric. So I think I kind of went you through this. You can have a user connecting in. You can have, a server connecting with lag. You can have a bridge network connecting with lag. You can have a router connected with lag. Now, here's a point. If I have a layer 2 bridge connecting in to the fabric, keep in mind that the fabric is layer 3 based. It means that any hosts behind the bridge will be learned on a layer 3 basis within the fabric. My fabric is not really populating any MAC tables because, once again, sorry for stressing this, but the fact being is that the fabric is a pure layer 3 fabric. So going to this gives you an example of actually 2 hosts connecting in, A and B, to the fabric. Now, obviously, the first thing you're going to have is your FIBs, your forwarding information base. So if you look at the fabric node 1, you would have for destination A/32, once again, it's a host route, the next hop being the lag port, for destination B/32 being a host route, next hop being the BGP port EF2. So eventually, you are going to actually be running EF1, EF2, EF5 down from a BGP point of view. Now assume you want to have, or then on EF5, you basically have the same thing, right? You have your destination A, next hop is the BGP port of EF4. And then destination B, the next hop is the lag port. All right? So obviously, the fabric can uniquely identify each lag, as I kind of went you through, even if it looks like an MLAG construct. So basically, then meaning that if, A wants to talk to B, obviously, by default, from a BGP perspective, the path would be EF1, EF2, EF5. And if B wants to talk to A, the path would be EF5, EF4, EF1. Now, by using actually some BGP additional attributes, you could eventually have traffic passing like this, because at the end of the day, it's a common lag. So it's a common lag between 2 elements, and this goes back to what I was saying about the fabric seen as a single entity, a single MAC address, which means that even if you had the access connecting into 2 different fabric elements, it's still a single lag. So, moving forward. Now, from a VXLAN point of view, so as I have been mentioning, this is a layer 3 fabric, which means that if you want to pass through a layer 2 connection being a VLAN, you need to use VXLAN overlay for that. What this picture basically shows you is, a couple of virtual networks, VNIs. You have the green and the orange one. Obviously, on the access side, the MAC routes are learned. Then, within the fabric itself, the MAC routes are distributed by EVPN. Now, here's the thing. How many of you are familiar with Exos? So today, VXLAN is done with what? OSPF, right? So we actually use for VXLAN the opaque LSAs, so a network LSA of type 11 to basically propagate your VNI, your VTEP information through the network. So this is kind of automated how I would, create a virtual network on access. I would use OSPF to just distribute that one into the core and basically have my peer doing the same thing at the far end. Now, as I have been stating here, ExtremeFabric is based on what? BGP, right? So if I kind of walk you through that, today we do the VXLAN with OSPF in Exos. If this is BGP, that means that we actually need to have, or we need to use MBGP for us to be able to propagate the VNI LTEP information in the BGP open message basically as a capabilities attribute, defining an AFI and a SAFI, so an address format and a sub-address format for the transport of the VXLAN. Do you guys follow me this? Come on. Okay, so key thing being is that obviously ExtremeFabric changes the story from VXLAN. It's based on BGP and MBGP for the VXLAN part. Otherwise, VXLAN is treated as a layer 2 connection, right? It's just an overlay using my fabric, my layer 3 fabric underneath to transport a layer 2 VLAN. So, ISSU. How many know what ISSU is? In-service software upgrade, right? So basically the ability for me to be able to transport traffic all the time within my fabric, even if I touch a single node element in the fabric, or even if I upgrade a complete fabric. So this, illustration basically goes through how that's done. So by default, you have on this picture traffic, passing between these two servers. The servers are lagged into your fabric. So first thing being is that I assume I want to actually, replace or upgrade a single element in the fabric, which means that I'm going to use LLDP or BGP to signal out of service. I replace that node or I upgrade that node, and I'm going to signal again in service. Okay, this is how I basically replaced a single node or upgraded a single node in a fabric. Traffic traversing server to server all the time. Now, what if I actually want to upgrade my complete fabric? So what I'll do is, this again, once traffic is traversing the fabric, I upgrade half of the fabric, being the red ones. And then after that, I actually upgrade the other half of the fabrics. So this is your ISSU-like function in a fabric due to the fact that it's half-meshed from a connectivity point of view. It's redundant connection on the access side. It's based on triple F switches, so fixed form factor switches, which would allow you to do that. Now, as you all know, that ISSU as a function as such is pretty complex and demanding in a chassis-based architecture, which means that looking at it from a fabric point of view, this is far more easy to achieve, actually. And obviously, this process is done from a management entity. So this is going to be command from some kind of a management platform that would then basically go through these steps for you. Once again, keep in mind that I have the RESTful API that do talk to the fabric itself. So, policy. So let me try to kind of walk you through this slide on a high level. So what this basically starts with is I have a sysadmin creating a VM, a virtual machine, and a virtual network. Now, for this given VM that I create a virtual network, I actually want to be able to, look at that VM, have a profile assigned to that VM, which means that if that VM were to move within my network, I would be able to move that VM, which means that I need to have a tracking mechanism in place. So we actually talk about something like XNV. You guys heard about XNV? Extreme Network Virtualization. What XNV allows you to do is to have basically a profile assigned to a VM. That profile would be then basically handled using NAC, because I know my VM's MAC IP, which means that once that given VM is going to move, I'm going to move that profile within my network based on the information I have for that VM. Now, to add on to that picture, obviously, I can monitor those VMs, so I can get port information, I can get VM location information, so on and so forth. But now, adding on to this picture, so I was saying that you can track a VM once a VM move. You would create your virtual network being your VLAN. Now, assume you have a VXLAN overlay. You basically want to have the ability to map or automate once I create a tenant VLAN, that tenant VLAN would be able to in some way signal or automate the VNI creation to be propagated through my network, which is automation, right? So for that, you actually have the EasyVXLAN app, part of X on a Python script basically doing that stuff for you. So what this picture shows you is automation. So we kind of, on a high level talk through that you can automate this based on VM environment. You can automate this based on bare metal servers because of your policy, right? You have Extreme management in place. So you have some kind of an API from Extreme management talking to the vCenter, being the VMware platform in this case. That's a well-defined API that we use with Extreme Connect. Now, many of you probably heard about the hyperscale, guys building with OpenStack. Obviously, this same applies to OpenStack. So Extreme Connect would allow you to have an ML2 plugin or API talking directly to OpenStack for basically creating the tenant VLAN to VNI mapping and configuring that or automating that from a configuration point of view. So this example was looking at this from a switch point of view, kind of a general point of view. Obviously, you could have your fabric in here. Doesn't matter. It's the same if it's a single switch or if it's a fabric. Okay? So let me get the build up here. So what this shows you is basically, as I have been talking about the RESTful API for Extreme management, this just shows you that you have your EMC up on the north here. Then you have your cloud connector. Basically have a RESTful API from EMC into the cloud connector. Further on an RESTful API into basically your fabric elements. And at the end of the day, you are going to push down the fabric configuration into each and every element based on this RESTful API. So to build up the picture here, so obviously, starting from the upper layer, Extreme management is used from a fabric point of view for zero-touch plus provisioning, which means that basically you bootstrap your elements. You do all the fabric management, monitoring, so on and so forth from Extreme management. You go to Extreme control, which is your NAC, right, where you do all your policies, all that stuff. You go to Extreme Connect, which is the API between Extreme management and any third-party devices. Like I described OpenStack, I described VMware, so on and so forth. It's just an API. Analytics, for the packet inspection, basically. And then the fabric being the underlay as I've been kind of walking you through. And then eventually you have open interface, both northbound and southbound, providing you with a variety of different things you can do end to end. So this really builds the complete picture that your underlay being the fabric, your overlay being then the virtual networks, and then on top of that one you have Extreme Connect being the API, Extreme Management being the GUI that you actually configure the stuff, and then Extreme Control being your policy and your NAC stuff. And then, obviously, you have your analytics as well. All right, ExtremeFabric. Did you get the picture? Does it make sense? OK. Point and leaf architecture. I don't think there's much new on this one. So actually, what this shows you is just a couple of boxes. The 870, I think, was covered already. So 870 really being the new 32 times 100 box. So you could build a spine leaf architecture like this. You see the 870, up in the spine. You have the 670. There's a typo here, so this should say actually 40 gig and 10 gig, not 100 gig. We don't have a 100 gig Vim to the 670. So it's uplinked with 40 and 10 gig. Then the 770 being a 40 gig switch. Then you have the 690, which is an upcoming switch, which is a 10100 switch, basically. And then you have the other 870, which is the 96X. So you see the 32C and the 96X of the 870. So what's the difference? The 32C is basically 32 times 100. So here's a breakout. You can see what you can do with that given switch. 32 times 100, 64 times 50, 128 times 25, 128 times 10, or 32 times 40 gig. So same hardware providing you with connectivity for all these different optic medias. Now, there's another SKU for this. This is exactly the same hardware, but this would allow you to actually start with only 800 gig ports, or 10, 25, 40, 50, 100 gig ports. And then rest of the 24 ports would be with breakout cables, 10 gig connections. Now, you could then add, with the license, always 6 ports to be 100 gig capable. So this is kind of going back to this picture, showing you that I could use the 87096X as a leaf device with a few hundred gigs uplinking. But I also have some, future proof on that one, because eventually I could upgrade that given device to complete spine switch with 32 times 100. Then we have the 690, which you basically have in 2 flavors, a copper and a fiber one. As you can see, it's 48 ports, 10 gig, and 6 times 40 or 4 times 100 gig being the uplinks. So this is a new switch coming late this summer. All right. That kind of concludes the ExtremeFabric presentation, some stuff around the spine leaf architecture.